Welcome to our webinar Selectivity in Line Protection. These sessions are made for those who start working or who are new in the field of protection and where a solid understanding of relay protection for distribution and transmission grids is essential. My name is Gerd Einsiedler and I'm happy to guide you through this second session of the webinar about selectivity. Some of you might already know me. I have been working in protection and automation for nearly 30 years. Since September 2023, I am part of Siemens Power Academy in Nuremberg as a certified trainer for protection. And today I'm introducing you to Selectivity in Line Protection lectures. How can we make the differential protection work selective? And what does the application look like in line differential protection? And since we receive one question rather often, yes, we will record the webinar and make the recording and the slides available to all registered participants. If you already joined one of our last webinars, you already know the Q&A field in this application. Please type in your questions to the presenter in the question field. We will answer your questions during the dedicated Q&A session after the series on 21st of June. In addition to me reading aloud your questions, you could also chat with our experts in the background. Please be aware of the following limitation. The chat is available in live mode only. Q&A questions will be answered via email if not managed during the live session. And just in case you are in full screen mode, press Escape to see the Q&A and chat box. And now let me introduce our expert, Professor Dr. Siegfried Lemmer. Siegfried Lemmer graduated and received his PhD at RWTH Aachen University. He joined Siemens in 1986. For many years he was head of product lifecycle management for protection, where he was deeply involved in the design of C-Protect 4 and C-Protect 5 relay families. Within a master course of power engineering at Brandenburg's University of Technology, Cottbus-Senftenberg, he presented lectures about protection for nearly 2 decades. In 2016, he retired from Siemens, but continued his university lectures. Siegfried, and now we are curious to learn more about the basics of protection technology focusing on selectivity. The stage is yours.
Hello and welcome to the differential protection session. This session consists of 4 parts. In the first part, I will discuss the general principles of differential protection, show how we can make the protection work selective. And then we have 3 parts where I show the different applications for line protection, for transformer protection, and for busbar protection. So let's start with the general topics. What is the principle of differential protection? Differential protection has a pretty easy principle. We draw a circle around our protected device, and then we measure all currents flowing into the device. And normally, according to Kirchhoff's law, the sum of all currents flowing into a device should be 0. We can calculate this sum by summing up individual sampled measured values or instantaneous current values. That is one possibility shown in the lower line of the yellow box. Or we can compute the phases, that means the amplitude and the phase angle represented as a complex value, and sum up the complex values. And these sum of currents, of all currents flowing into a device, is called the differential current, either in phasors or calculated with instantaneous values. We can do that phase by phase. That means we have to multiply this, what you see now, by 3 do the same thing for the other phases as well. And for a healthy device, we learned this differential current is 0. What is now going to happen if we have a fault? A short circuit. That means from one phase we have a current flow either to ground or into the other phase. Of course, in such a situation, Kirchhoff's law is also valid, but the fault current flowing to ground or into the other phase is not measured. We have no current transformer at the fault location, and that disturbs the equation. And that means in case of a fault, we suddenly have a differential current. That means the differential current is a good indication for a fault. But you see here, I wrote theoretically, of course, if you program such a thing, you cannot ask, is the differential current exactly 0? It will never be exactly 0. That means you must always allow a certain deviation from 0, and we call that threshold. That means the principle is we calculate the differential current and we compare this current with the threshold, and if the differential current is above the threshold, then we say, okay, there must be a fault in the protected zone, and if the differential current is smaller than the threshold, then we say, okay, the device is healthy. So the problem is the threshold. What is the correct value for the threshold? And the issue there is we cannot take a fixed value. If we make the threshold too small, then the protection becomes very sensitive, but we may have wrong trips. If we make this threshold value too high, that means we trip only if we have a significant differential current, then we may not have sufficient sensitivity to catch all faults we want to catch. And I would like to illustrate that a little bit more using two examples. So here I have again this equation. We trip if the differential current is above the threshold. You see in the yellow box the equation just for a two-ended line. There we have to sum up two currents, either as phasors or as instantaneous values. And the first case I'd like to discuss is a fault, maybe a resistive fault on a line, on the protected line. In this case, we expect that our protection relay should trip. So what happens? We measure the currents at two ends of the line. Short circuit currents comes from both sides. That means both current transformers measure a certain current flowing into the line. Fault current 1 on the left side, fault current 2 on the right side. And from that we calculate the differential current. We assume they are in phase, so we can just simply sum up the two currents. That means the differential current in this case is equal to the fault current. And now that means, for instance, if we have a resistive fault, the fault current can be pretty low. And let's assume in this case we have a fault current maybe of 300 or 400 amps. That means our threshold must be lower than the lowest fault current we want to catch. That means if we want to catch a fault of 400 amps, our threshold must be lower than this value of 400 amps. That is one case. Now the other case, and this other case is normally the more critical thing in differential protection, we have an external fault. That means a fault outside the protected zone on the next zone, and there our protection relay should not trip. And what is the situation there? We have a short circuit current through our protected line. That means on the left side, the current transformer sees a fault current, this through current. On the right side, it sees the same current flowing out of the line, so it sees minus IF. From that, we can calculate the differential current, IF minus IF, which is 0. No trip, that is fine. But In real life, of course, it will not exactly be zero. In real life, we will, for instance, have measuring errors in our current transformers. And that means the measurement on both sides will not be exactly the fault current. It will be, as indicated here, the fault current plus or minus a certain measuring error. I call it here delta I. As long as the measurement error is the same on both sides, it will have no impact. The differential current will still be zero. But we can, of course, also have the case that the left side current transformer has a negative measurement error and that the right side current transformer has a positive measurement error. And then the differential current is no longer zero. If we, for instance, assume a 5% measurement error, and one has minus 5%, the other has plus 5%, the result will be that we have a differential current which is equal to 10% of the fault current. And now imagine if we have, for instance, a fault current of 10 kiloamps flowing through the cable, and 10% of 10 kiloamps would be 1000 amps. That means we would, in this case, see a differential current of 1000 amps. That means our threshold value we use for the differential principle must be higher than 1000 amps. That means on the left case we said it must be lower than 300 amps, and on the right side we say it must be higher than 1000 amps. And the result of that is this threshold value must be adapted to the fault case. That means in differential protection, we calculate the differential current and compare it with a value which has to be adapted to the fault case. And there are different possibilities to do that. The first thing I would like to show is the traditional concept you find in many differential protection applications. That is the use of the so-called restraint current. And that means we calculate a restraint current just by summing up all currents, by summing up the absolute value of all currents. That means without taking the sign and the phase angle into account. And this restraint current is an indication of how much current is flowing there. And that is used to adapt the threshold value. And what you normally find there is a diagram like this. That means you have on the horizontal axis this restraint current, which is an indication for the amount of current on the line. And on the vertical axis, you have the differential current. And then you define in this plane a tripping area. It can look like this orange area here. You see in particular applications it may look a little bit different, but the idea is always the same. And that means as long as you have low currents flowing, that means the restraint current is low, then the limit where the tripping area begins, this threshold value, is lower. And if you have high currents flowing, think about our through fault, then the limit where we do the tripping is higher. So that is just given by this characteristic. If we have a fault in the protected zone, then the differential current is equal to the restraint current. Then we are on this red dashed line. That is the fault in the protected zone. And what you can see also from this diagram is if you have a fault in the protected zone with a very low current, you are still in a white area, it will not trip. That means with this principle, you have a certain level of fault current which must be there so that the protection will react on that. So for very, very low currents, it will not see the fault. That is called the traditional differential protection concept. We use it in our relays for transformer protection, for busbar protection, for generator protection. For line protection, we are going a different approach, because in line protection, we often have to deal with different fault mechanisms, with resistive faults, and there we introduced already with CProtect 4 relays a different approach. This approach is an adaptive concept. It goes again back to the original idea. The question is, what can be the maximum differential current in a certain operating state for a healthy line? That means in this concept, the protection relays permanently measures all the currents and then estimates in this operating states we actually have. It can be a load state, it can be an internal fault, it can be an external fault. In this state, what can be the maximum differential current we can have? Add a little bit of security to that, and if we then calculate a differential current which is higher than this value, then we say it must be a short circuit in the protected zone, then we trip. And with this concept, and we will discuss a bit more in detail what are the different sources for differential current on a healthy line. With this concept, we come to a very sensitive and reliable protection of lines. So, as I said, that's an alternative to the traditional concept. In general, if we compare differential protection with the other protection principles we discussed, like overcurrent protection or distance protection, it has some advantages, but you will see it also has some disadvantages. What is the advantage? It's a very simple principle. No complicated algorithms for impedance measurement. We just measure the currents. We have a clear definition of the protected zone. That is really a nice feature. Remember this story, this discussion for distance protection about how long is the reach of the zone, it's influenced by measurement errors and so on. You can forget all this. For differential protection, it protects the line or the transformer from one current transformer to the other one. And you can also make settings which allow you a very sensitive protection. That means we can catch resistive faults. But it also has some disadvantages. Remember, in overcurrent protection and distance protection, the protection relay, first of all, looks at its own line, but it also looks a little bit into the next line. And if there is a protection failure on the next line, our protection relay sees also this short circuit on the next line, sees that the relay on the next line does not react on it, and can then serve as a backup. That's not possible with differential protection. Differential protection just looks at its own line or transformer and is not interested in anything else. That means you must think about additional functions to do the backup. Then if we apply differential protection to lines, then we need a data exchange between the two ends of the line. And this data exchange, imagine if you have a long line, 100 kilometers, you need a reliable data exchange between the two locations. And that can be a thing which is not in all cases very easy. And there is also a certain risk that we react sensitively on saturation. Saturation is an issue where we have to live with. Overcurrent protection and distance protection tend to do underreaction. That means to have a delayed tripping in case of current transformer saturation. In differential protection, we have a certain risk of a wrong tripping in case of saturation, and we must provide additional measures in the protection relays to avoid these problems. So that was a short introduction into differential protection, and in the next chapter I would like to talk about line differential protection. Let's have a look into line differential protection. You see here again in the yellow box the equation how we calculate the differential current, and I would like now to show the different situations we have to distinguish. The first thing is the normal operation. In normal operation we have a current flowing, a load current flowing through our line or our cable, and both current transformer measure the same current. On one side it flows into the line and on the other side it flows out of the line. So the differential current is load current minus load current is 0. Then we have the situation with an internal fault. That means we have a short circuit on the line between phase to ground or between phases, whatever. Remember, this principle is always done phase by phase. And what is the situation there? We have short circuit current flowing into the line from both sides. That means both current transformer measure incoming current, and if we sum up these two currents and calculate the differential current, we find that the differential current is equal to the fault current. And then we have this other case, this external fault, and typically that is the most difficult thing for a differential protection, not to react on an external fault. For the external fault we have a strong current flowing through the line. It's similar to the load situation, but the current level is much higher. That means all measurement errors tend to be much higher. Theoretically, in this case, the differential current is 0. Practically, and we will see that on the next slides, we have to make up our mind what can be a differential current in this situation. I mentioned already in the first part, we use in our line differential protection not the traditional differential current and restraint current characteristic. We have an adaptive scheme. That means, that is again the principle, we trip if the differential current is above the threshold, and the threshold should be the differential current without a fault on the line plus some security margin. And now we have to discuss how can we estimate what the maximum differential current on a line can be without a fault. And this differential current we can measure without having a fault consists of different parts, and we will look at them one after the other. The first thing is the capacitive current. That means the line, or especially if it is a cable, has a certain charging current, and this results in a differential current, as we will see in a minute. Then we have current transformer errors, measurement errors in the current transformers. They can generate a differential current, as we already saw in the first part. Then we can have some signal distortion coming from saturation or DC components or whatever. They can generate differential current. And there is a last thing which is especially required for line protection. Line protection has to measure the currents on both ends of the line, and these values have to be exchanged via a communication. And this communication can have some delay. Let's assume we have a delay, for instance, of a millisecond, and that means the incoming values in a protection relay from the other side should not be compared with the actual values, but with the values a millisecond ago on our own side. That means a delay time in the communication can be compensated, but sometimes we have a certain jitter or unknown delay time there, and that can cause a certain synchronization error. We will see also the result on that. So let's start with the charging current. And the easiest way to think about the charging current is imagining that the right breaker is open. We calculate the differential current is I1 plus I2. If the right breaker is open, I2 is 0. That means the differential current is I1. And especially if we have a cable, we have a certain charging current, and that is the current the relay on the left side sees, and that is automatically the differential current. Because in this case, right breaker is open, differential current is equal to I1, and I1 is equal to the charging current. And just to give you an indication of about how much that is, I have here just an example for a 110 kV cable, in this case 16 kilometers long. I took a cable with a cross section of 240 square millimeters, and with this formula you can calculate the charging current. That means in this case we have a charging current which is equal to the differential current of 99 amps. That can easily be calculated by the protection device. You only have to tell, as a user, you have to tell the protection device how big the charging current is. Second thing is the current transformer errors. That means we are talking now about this part here in the equation. And the current transformer errors are especially critical for external faults. For this situation, we have a fault on the next line and we expect our relay not to trip. We already discussed the ideal case. One side measures fault current coming in, other side measures the fault current going out. With current transformer errors, we do not measure exactly the fault current. In this case, I say we measure 1 plus relative fault on the left side multiplied with fault current, the same on the right side. As long as these measurement errors are identical, that would be the result. The differential current is F1 multiplied by with the fault current minus F2, error on the right side, multiplied by the fault current. If F1 is equal to F2, it's not a problem. The differential current is again 0, but we want to have an estimation of the maximum differential current we can have. And for that we have to take the worst case. And the worst case is that F1 has a positive sign and F2 has a negative sign. And for instance, they are equal. Worst case would be F1 is equal minus F2. We call it F. And then the differential current would be 2 times F multiplied with the fault current. That would be an estimation of the differential current measured by our protection system on a healthy line. We should not trip on that. Sometimes it's not possible, as shown here, to describe the behavior of the current transformers just with a simple error value. The current transformers have the problem, or have the feature that the relative error increases with increases current. That means as long as you have load currents, you are in a range of maybe 3% error. And if you have short circuit currents, if you have higher currents, then the relative error can go up to 10% or even higher if you have very high currents. That means the error curve of a current transformer, and from that also the possible differential current resulting from that, looks like that. And that cannot really be described just by one simple error value. And for that reason, we often used a stepped characteristic. That means we say in the range of load currents, in the low area between zero and nominal current, we can assume a relative error in the current transformer of maybe 3%. And if the currents are higher, then we assume a relative error of, depending on the type of the current transformer, we assume an error value of 10%. That is a bit a more sophisticated thing. Of course, as a user, you don't have to deal with this diagram. You only have to tell the relay these two error values. You have to tell the relay what is the current transformer error in the load range and what is the current transformer error for short circuit currents. And then the relay can, during its operation, permanently estimate what is the maximum differential current resulting from these current transformer errors. Now let's have a look at the synchronization errors. Where do they come from? As I already said, we have to exchange information from both sides, and I can show you one example where I simulate a fault. You see here in this diagram the two blue curves, they are nearly together, so that are the two current values on both ends of the line. But now I assume that depending on the communication between the relays where we have to exchange the values, we have a mismatch of 1 millisecond coming from jitter or wrong compensation or whatever. That means when we calculate the differential current, we compare our current we receive from the other side with the current value on the local side, but with a mismatch of 1 millisecond. And for that reason, you see in the diagram two blue curves, which are shifted just by 1 millisecond, and the red curve shows the differential current resulting from that. That means theoretically the two currents on both sides are identical, but due to the synchronization error, we calculate a differential current, which also has to be taken into account. That means in this case, you have to tell the relay what are the features of your communication system, what is the maximum synchronization error we can expect, and from that the relay can then permanently estimate the possible differential current resulting from that. If you have a direct optical fiber connection, it's a very easy thing. If you go through a communication system, it can be a bit more complicated to find out this possible mismatch, but it is required to have a reliable operation to avoid wrong trips, and on the other side to be sensitive. Concerning the algorithms, I said in the beginning, you can apply the differential protection principle either on individual samples, on instantaneous values, or on phasors. So what can we do in line differential protection? Also there we can do both. Theoretically, we can use individual samples. That means, let me say, every half millisecond, I take the sample from my local side, compare it with the sample coming from the other side, and calculate the differential current. Experience shows for line differential protection that is not a very reliable approach, and so for that reason we make it a little bit more robust by integrating, not using one sample, using a few samples. That means we integrate the current values across a few milliseconds, typical 4 or 5 milliseconds. Integration of current is typically the charge from the physical point of view, and for that reason this approach is called the charge comparison protection. But it's from the behavior, it's very similar to comparing instantaneous values. The good thing is you don't need any long data windows. That means you collect just data across a few samples, and from that you can then calculate the differential current, evaluate what is the maximum differential current we could have on a healthy line, and if it is higher, you trip. With this approach, with this algorithm, short tripping time is possible because you need very small data windows. Unfortunately, you cannot suppress harmonics or DC components. So for that reason, these algorithms cannot have the full sensitivity. They are fast and they are typically tuned to catch clear faults with high fault currents and trip them in a very fast way. On the other side, we can calculate the phasors. That means we need a longer data window, typically one period, 20 milliseconds or 16 milliseconds in a 60 Hertz system. Calculate from that the differential current and then apply the differential principle on phasors. That has a few advantages. By the application of these phasors, we have pretty good filtering. That means we can filter out all disturbing things like harmonics and DC components. And for that reason, we can make a very sensitive setting. But as we need longer data windows to calculate the phasors, the whole thing is a bit slower. And that means these two approaches complement each other. And for that reason, we typically have both approaches running in parallel in line differential protection. That means we have a charge comparison and a phasor-based algorithm running in parallel. The charge comparison will enable fast tripping for strong faults, and the phasor-based algorithm will then catch the faults with lower fault current where the higher sensitivity is required. And for these faults, the speed is not the big issue. That means it's not a big disadvantage that this algorithm is a bit slower. That was a short look into line differential protection. The next topic will be transformer differential protection.
Thank you, Siegfried. That has been an interesting session. Dear auditorium, thanks a lot for your questions. We will answer these in the Q&A session on 21st of June. If questions come into your mind later, or you would like to go for more details, please visit our training platform at Siemens Power Academy. I'm sure you will find the right information and the right training. The access to the recording and the slides will be sent to all participants. Thank you very much for your active participation. It was a pleasure for me to guide you through the session on selectivity in line protection. In this session, we learned how differential protection can work selective and what the application looks like in line differential protection. I am looking forward to meeting you soon in the next session of selectivity in line protection on June the 20th, which will focus on what does the application look like in transformer differential protection and what does the application look like in busbar differential protection. Stay safe and sound, take care, and goodbye.